let us recall what we have mentioned in the beginning of the course. What did you say? We want to study the set R, that is done by studying first of all subsets of R, power set of R, then we mentioned about some nice subsets of R. After that we said we want to study all functions between subsets of R of the form U subset of R. We want to study all functions of this form. Then we have said as a first step we study functions whose domain is the set n, the set of natural numbers, and these are called sequences in R. And then we have spent many classes understanding the notion of sequence of real numbers, some field classes, some results as I said. Now, assuming we have sufficient experience with the sequence of real numbers, we will now proceed to the case where these functions, the domain is not just n but any arbitrary subset of R. So, let me replace this again by U. So, this notation is only to say that this set U is actually subset of R. Once we know that it is all subset of R, this is not necessary to remind, this is only to remind yourself that whatever I am writing, it is subset of R. So, because I said so many times, I am assuming you will remember this, so I am removing this. So, now we are trying to understand set of all functions from a subset U of R to R. Let me denote this set of all functions by this f of U. Given a subset U of R, U is subset of R. Given a subset U of R, we denote the set of all maps from U to R by f of U. Nice. So, now what we do is we will repeat whatever we have done for sequences. What do we do for that? In sequences this was n. Then we said if I take any set B with some structure and a set A, the set of all maps from A to B will induce a structure from the structure of B. That is what we have said for sequences. B was R there, R has addition, multiplication, additive inverse and multiplicative inverse. Then the A was n. So, we have said that the structure on R induces structure on set of all sequences. So, that is how we have seen the notion of addition of two sequences, multiplication of two sequences, additive inverse of sequence, multiplicative inverse of a sequence. So, we will do the same thing here also. The structure on R should induce structure on this f of U. So, let me remove this. Now, R has addition, multiplication, additive inverse, multiplicative inverse. So, we expect that this will also have similar structure. So, we will write down the maps associated to that f of U cross f of U to f of U. So, an element f and element g goes to f plus g. This is a structure map on this set induced by the structure map of R, the additional structure map of R. So, this should be an element of f u. By that we mean f plus g is a map from U to R. How is it defined? An element x goes to f of x plus g of x. That is how we are defining the sum of two functions from U to R. Similarly, one can define multiplication f comma g is mapped to f dot g U to R is a map that takes x and assign the element f x dot g x, the multiplication of these two elements. F x is an element of R, g x is an element of R. So, the product makes sense for any two elements of R, and this is how I am defining the product of two functions. And one can talk about the additive inverse. Given an element in f u, say function f is a function, f is an element in f u which is a map from U to R. So, for this we assign minus f. What is minus f? What should be minus f? It should map from u to r that take x and send it to minus of f of x. Similarly, multiplicative inverse also we should be writing induced by the multiplicative inverse of r. So, let us take fu. We should assign a map in fu. So, take a map f, assign it to 1 by f. How is it defined? 1 by f is a map from u to r such that for a given x we assign the element 1 by f of x. Here observe, unless fx is non-zero, this does not make sense. So, this map whatever I am writing here, I cannot talk about this map for any arbitrary f. There may be f for which f of x is 0 for some x in u. So, such functions f we ignore, we do not consider the function f for which fx is 0 for some x. After ignoring the such elements, the resulting set is what we are writing as fu star. What is fu star? An element f of fu is an element of fu star if fx is non-zero for every x in u. So, this is a subset of fu. For such elements one can talk about 1 by fx, because fx is non-zero, 1 by fx is an element of r, and I am denoting the map x is mapping to 1 by fx. So, one should also write down fu star here, but it is okay, it does not really matter. The structure maps on R, induced structure maps on fu. We have 4 maps: addition, multiplication, additive inverse and multiplicative inverse. Now, this is fine. So, now what do we do after this? So, recall what we have done for the case of sequences. After we define the notion of sequence in R, we said we want to focus our attention to certain special class of sequences that we have mentioned as Cauchy sequences, monotone sequences, bounded sequences, convergent sequences. These are the 4 class of sequences. I mean, it does not look like this is Cauchy, but there are 4 class of sequences we have mentioned, and that is what we have worked on for the last few sessions. Okay. So, let us ask, how did we come to the conclusion that these are the candidates that we need to focus? We have made use of the previous structure. When defining the notion, we have the notion of infimum and supremum. Using that, we said for a sequence it is good if there is an element, if there is a single element in R that describes the sequence in a nice possible way. So, that is where we came to the notion of convergent sequences. So, using the previous idea, we focus our attention to convergent sequences. Now, using the idea of these sequences, we will focus our attention to functions on U to certain special class of functions. So, now an element here is a function from U to R. Here we have sequences. Now, it is not very clear how do I relate these two notions. I mean, convergence sequence also it was not very clear. Convergence thing was it was mentioned for sequence, but previously we had only set. So, it may not be very straightforward when you see for the first time, but for the second time it looks very natural. So, let us take the following situation. Let us take a map f from U to R. Now, our idea is to involve sequences somehow in this setup. Only then we will be able to make use of the sequences, the idea of sequences we have studied before. Observe the following. Suppose we take a sequence in U. What is it? It is a map from N to U. That is all the sequence is, right? Now, if we compose with this map, a map from U to R, which we have written by as F, this composition gives a map from N to R. So, it is a sequence in R. So, what do we have? Given a map from U to R, for every sequence in U, we get a sequence in R. So, let me write down that. So, sequence of U is mapped to sequence of R. This map we are denoting by F hash. This is what we have using the notion of sequences in U and R. At this stage it was not very clear how do I make use of sequences. Now I have some notion of sequences here, now also I do not know what to do from here. So this you might have seen in previous class also, you will see in future also many times on a daily basis. Let us try to recall some notion of linear maps or group homomorphisms in the group theory course or any other course. So let us take two groups H and G. What is the morphism from H to G? Whenever we are talking about map between groups, we do not allow all maps between them, we allow maps that satisfy that are compatible with the structure given on both domain and range. Not only for group theory, one can talk about linear maps. Take two vector spaces V and W. Maps that we are interested are such that this map should be compatible with the structure of V, in the sense f of x plus y is equal to f of x plus f of y and something else. So similarly, these two have some structure, in the sense that there are some special elements in SU, namely bounded sequences, monotone sequences, Cauchy sequences, convergence sequences. So one reasonable thing to ask is that this map we are calling it as special if f hash, this map is compatible with those class of sequences, not necessarily all at a time. We will take one class of sequences, let us ask map that is compatible with these class of sequences. So that gives us 4 special functions. So let me write down that. So first of all, what is it? Boundedness, that present boundedness, then about monotone, then convergence, then Cauchy. So we will try to focus our attention to functions that preserve this property, in the sense, suppose xn is a bounded sequence in U, then f of xn is a bounded sequence in R. This kind of functions are the first class of functions that we want to focus our attention on. So this is done. So let me recall one more time. A function f is said to be nice with respect to this property if for every bounded sequence xn in U, the image is a bounded sequence in R. That is the first class of functions. Second, you might be already guessing what I am going to write. If xn is a monotone sequence, then the image is a monotone sequence. So f is said to be nice with respect to this property if for every monotone sequence in U, the image is a monotone sequence in SR. For every convergence sequence in U, xn converges to x, this is happening in U. For every convergence sequence in U, we want the image to be convergent as well. F of xn converges to f of x. Similarly, xn is a Cauchy sequence, then we want the image to be Cauchy sequence. So this says there are 4 special class of functions from a subset U to R. Now let us recall these properties first. So we have already mentioned that boundedness is actually ignoring the real structure of the sequence, in the sense 2 sequences may have same bound, but one of them is convergent, the other is not convergent. So boundedness is not a good candidate to spend time on, at least for now. So let us keep this aside. We will be interested in this kind of functions also, but for now let us keep this aside, because if I am working only about the boundedness, the structure of function is lost, because all this says is about the image and this is not that bad in the sense, look at the bounded sequences. Bounded sequence, if they are monotone, then we know they are convergent. So if you add extra condition for these functions, we might get some nice structure, but for now just bounded functions doesn't seem to be very interesting for the reason that I mentioned just now. Now let us look at monotone functions. Again, monotone sequences are, as I said in the previous sessions, they are too strict to handle. In the sense, they want to be very nice from the very beginning, either increasing or decreasing from the very beginning, and any small corrections, any small manipulation at the beginning of the sequence or at any place will not retain the monotonicity of the resulting sequence. So because they are so rigid, it is not very comfortable to study the functions as the first step. See, we might have, as in the case of bounded functions, we might have to study, we will study monotone functions, but not in the first not at the first step. See, we will do what is slightly comfortable for us. We should be able to play slightly here and there. So these are too strict, this is too strict, and this is actually ignoring the function itself. It doesn't matter what the function is, only the image of the function is what is relevant here. So these kind of people we will keep aside. We will come to this maybe later part of the course whenever there is a necessity. So now let us proceed to the convergence. Convergence, we don't see any issue as of now. So let us first focus on convergence. Function f being nice with respect to convergence if this happens. What is this? For any convergence sequence in U, we have the image is a convergence sequence, of course in R. See, observe the following. Whatever I am saying about boundedness, I said boundedness, I said this is monotone, I said this is Cauchy. I did not mention that this is bounded in U, this is monotone in U, this is Cauchy in U. If I say this is sequence in U, that is sufficient. But for convergence, that phrase is not sufficient. If I say a sequence in U that converges, that does not say that this x is an element of U. This more explanation we will see it later part of the course when we talk about metric space and all. We will see this, but as of now it is not very clear. If a sequence converges in U, this element should be in U. It is not very clear. Do we have some examples for that? Think about rational numbers. In the assignment we have that whatever I have given, there I have mentioned that root 2 is not a rational number, but one can find a sequence of rational numbers that converges to root 2. So similar, you can relate that here. This xn, think of it as sequence of rational numbers, and this x as root 2. So there may be sequences that converges, this sequence totally contained in U, but the limit may not be contained in U. This kind of thing we have seen already about root 2. So here what I am asking is, I want the sequence to be in U and also the limit to be in U. Both of them, both the sequence and the limit should be in U. Only then, yeah, that is what I am asking. That is what we are concerned about. In this case, we say if this implies this, a convergence sequence in U should give a convergence sequence in R with this being the limit. Then we say that f is nice with respect to convergence. Actually this nice thing I am using many times, but at this stage we have already a name. We do not have to do any give any nomenclature, extra nomenclature. This already has a name, that is called we say that this map F is this if for every convergence sequence in U the image is a convergence sequence with this being the limit. This is about convergence. So, these two okay. So, this is it is not really taking care of the full function, only the image. So, we are keeping this aside. This is too strict to handle, we are keeping this aside. So, now we will focus on these functions that preserve convergence. F from U to R is a continuous function if for every convergence sequence in U the image is a convergence sequence in R. Again I am saying, I will say some more times, finitely many times, that this continuity should start with this being the situation. We want a convergence sequence in U, which means the limit should also be in U. See, this seems to be unnecessary for some of you, because whenever there is convergence, I can talk about convergence only when there is an element in R, not in U. As I said, there may be sequences in U that converges, but not to the element, but the limit point may not be in U, right. So, this is about the continuity. Now, if you observe, it looks like we are doing the same mistake that we have done for monotone sequences. What is the mistake? We wanted the sequence to be very nice from the very beginning. Here we are asking the same thing. We want all sequences in U to be convergent. Maybe we should give some relaxation and ask, at some places it may go wrong, that's okay for us. Yeah, if you allow some restriction, if you allow some relaxation, we might be able to do some more construction and be slightly more happy. So, further then we allow some relaxation, in the sense that a function f being continuous means this I cannot change, but what I can ask is, maybe I can focus on functions that are continuous at a particular point. I am not mentioning about the other points of U. Given a point in U, one can talk about functions being continuous at that point. So, what should be the definition? Whatever I have written here. For any sequence in U that converges to this special element x, the image should converge to f of x. This kind of functions are what we are calling as functions that are continuous at x. See, what is the benefit by allowing this kind of functions? There may be functions from U to R that are continuous at some points and discontinuous and not continuous at some points. That is okay for us. When can we realize that this is okay for us? When we think about integration of functions, we will see that the functions that we want to integrate are not actually very nice, not very continuous, but at some places we give them some freedom to behave slightly badly. Still they are integrable. So whatever I have said here, allowing some functions to be not very nice is actually a good thing when concerned about integration. So that we will anyway see again. I will repeat the same thing that whatever I have done, whatever I have said, maybe in next when the integration part comes. Yeah, so that is about continuous functions and functions continuous at a point in U. That is about the definition of that. Now, remember what we have done for this case of sequences. Once we define sequences, then after that we have defined the sum, the product, root inverse, multiplicative inverse. Then we mentioned that there are 4 classes of sequences that we are considering as special: monotone, bounded, convergent, Cauchy. After this, what we have said is, we want the structure on SR to induce structure on these sequences. In the sense, if I take two convergent sequences, the sum should be convergent. If I take two Cauchy sequences, the sum should be Cauchy. I mean, that was not our idea to insist that it is convergent, that was not our idea to force that it is Cauchy or convergent, but we have realized that it's actually the case. We didn't force it, we have observed it. That is the difference you should understand. Similarly, here also we will do the same thing. For functions on U, we have this structure. For functions on U, we have this structure: addition, multiplication, additive inverse and multiplicative inverse. So, what we ask is the following: does these maps restrict to give map between continuous functions on U? I did not mention what is the notation for the set of continuous functions on U. We will write down that now. So, CU is the set of all continuous functions from U to R continuous. If you want to specify a point, we will just put a x here, CXU, set of all functions continuous at x belongs to U. This is the notation. Now, so first thing we want to do the following: if I take two functions that are continuous, if I take two functions from here, see, let me take two functions, f and g belongs to Cu. As I said, this is by definition subset of Fu. Here there is a structure of addition. So, f and g being elements of Fu, one can talk about f plus g being an element of Fu. The only question now is f plus g an element of Cu? So who will check that sum of continuous functions is continuous? You do not have to spend so much time on this, you have already done this, or I am assuming you have already done something that gives this as a easy consequence. Look at the case of sequences. Given two sequences that converges, the sum is a convergent sequence. One can just apply that idea here and prove that if f and g are continuous functions, the sum is a continuous functions. That I am leaving as exercise. If this is very difficult, I would not have given this as an exercise. Whatever I have done for sequences, or whatever you have done for sequences, checking the sum is convergent and all that, we will just use it directly here without thinking so much. Similarly, if f and g are elements of Cu, because C is subset of Fu, f and g are elements of Fu. Fu has a structure of multiplication. So, one can talk about multiplication of these two functions. This is an element of Fu. Is the actual element of Cu? That is the question. If I take two continuous functions, is the product a continuous function? Is the sum a continuous function? If I take a continuous function, is the additive inverse a continuous function? If I take a continuous function, is the multiplicative inverse continuous function? But for this to make sense, f should be non-zero, it should not be 0 anywhere. In that case, is the 1 by f a continuous function? These are the things that you need to check. And similarly, you can check for this also. If f and g are continuous at a point x, it may be very bad outside the when we are, it may be very bad on the whole U, but at x it may be nice. If f and g are elements of this, is the sum an element of this? Is the product an element of this? If I take an element from here, is the minus f an element here? If I take an element from here, that is nowhere 0, is 1 by f an element here? These are the questions that we need to ask. It should be straightforward from the whatever I have done the sequences. We will just copy paste that here and you will get this. Now, that is all about continuous functions. Now, we need some examples now. This also, as I said in the end of the previous session, whatever you have done for sequences, same ideas we will apply here. I don't, the same ideas we will apply here. What did you do for examples in the case of sequences? We took only two examples of sequences. We added, multiplied, additive inverse, multiplicative inverse, did all those combinations, and we got some examples. We do the same thing here also. We don't have to think so much. Very small examples. If we come up with 2 examples, that is done. We can use them again and again and produce as many examples as we can. So let us take this example. What example should we take? That also we don't have to think so much. Let us just copy whatever we have done there. What are the examples of sequences we have taken? First is constant sequence, everything is going to 11. Second thing is identity sequence, an is equal to n for every n belongs to n. So let us do one by one. Let us take a function f from u to r that sends every element of x, that sends every element of u to say 7. 7 is a nice number. Numbers are nice. You cannot do anything about it. So this is a function. First question is it a continuous function? Right. So we have done this kind of checking in convergence also. So we have given some sequence that an is equal to 11 for every n belongs to n. We have checked the convergence, right? So here also we should do the same thing. We should check for the continuity, because we have the convergence was working properly. Maybe this also will work properly. We will check. We don't have to assume anything. I mean, it's easy to check, so we will check that. Or because it is easy to check, I am checking. Anything that is difficult, I will leave it to you. Also, what do I need to do here? I should pick an element x belongs to u and take a sequence xn that converges to x. xn is a sequence in u that converges to this element x. Now what I should do is I should apply this function f for this sequence and this, and then check whether the sequence is convergent or not. So let us do this. F of xn is what? It is a constant function. Irrespective of what xn is, this is always 7. So the sequence is the constant sequence 7. Constant sequence is convergent, converges to 7, and this 7 is actually f of x. So what did I observe? For if you fix an element x belongs to u and a sequence that converges to x in u, then the image sequence f of xn converges to f of x. What does it say? Every constant function is a continuous function. Nice. So let us so this example we have copied from sequences idea, and luckily this worked. Let us copy the second example. What is the second example? Identity sequence. So here let us do identity function. F from u to r, an element x belongs to u is mapped to the same element. See, as I said, u is subset of r, x belongs to u plus x belongs to r. So this map makes sense. It's continuous or not, that is second question, but this map makes sense. Now how do I check the continuity here? I need to fix an element x belongs to u and take a sequence xn that converges to x. What I should do here is I should apply this map f to this sequence and see whether the image converges to f of x. So let us write down what is f of xn. What is f of xn? F is a identity sequence, identity function. F is identity function. So f of xn is equal to xn. So this sequence same thing as this sequence. We already know xn converges to x. So this converges to x. We already know fx is equal to x. So this is equal to f of x. So if we know a sequence, a convergent sequence in u, the image is a convergent sequence in r. What does it say? Identity function or continuous? See, one should be very happy at this stage because of the following reason. Identity function here is continuous, but identity sequence was not convergent. You might remember that. So maybe we should celebrate this situation where whatever was not working, whatever was not very nice for the convergent sequences, the similar example is nice here. So now we got See, look at the previous case. There was only one convergence sequence was there, the constant sequence. Here we have two functions that are continuous. Celebrate this situation, and after the celebration we will proceed further. So we have two continuous functions. What do you think we should do now? Apply the operation that we know again and again and produce so many continuous functions. So let us do that. First of all, what operations do I know? Addition, multiplication, additive inverse and multiplicative inverse. So let us do that. So let us add two continuous functions. So f plus g, for convenience I am using the same f, same letter f. I am using the same letter f for this and this. So let me write down this as g, just so that it is we differentiate that. So everything is now g of xn, g of xn. I used only at 3 places, so these 3 places I have changed. So f is the constant function, g is the identity function. So f plus g should be a continuous function. So a function h from u to r defined as x goes to x plus 7 should be a continuous function. This h whatever I have written here is simply f plus g. Addition we have done. Now we will do multiplication. Given a function, given two continuous functions, the product is continuous function. So f and g, f dot g from u to r that assign x to 7x is a continuous function. So we have how many continuous functions? 1, 2, 3 and 4. Let us do multiplication for other continuous function. What is it? I want to multiply this function by itself. X goes to x times x, that is x square. So a function from u to r defined as x goes to x square should also be continuous, because x goes to x is continuous. The product of that function with itself is continuous. So x goes to x square is continuous. As I said, this is continuous function, this is continuous function, the sum should be a continuous function. This is continuous function. I can take product of this function with this function. What do I get? X goes to x cube. I can take one more time 4, one more time 5. What does this say? The function x goes to x power n is continuous for every n belongs to n. We see just with 2 examples of continuous functions, we have so many examples of, we are getting so many examples of continuous functions. So at least we have this many continuous functions. This is the fun didn't stop here yet. One can take sum of this and this. So x goes to x plus 7 plus x power n is continuous. X goes to x plus 7 plus 7x plus x power n is continuous. In general, x goes to a0 plus a1x plus a2x square plus so on plus an x power n is continuous for every n belongs to n and an belongs to r. You might already recognize this function. What is this? Polynomial function. Let me write down this u and r also. So u to r. So what did we see? Every polynomial function is a continuous function. Where do we start with? 2 examples of continuous functions. Just doing these operations again and again, we got many examples of continuous functions. So let us use the other structure of R to produce more continuous functions. Right? This is what we are supposed to do. Using the structure of R, we will produce more continuous functions. So what structure did we use till now? Only these 4 structures. There are other structure also. What is it? Order. In the sense, given 2 elements, I know when one is less than the other. For any 2 elements, I know one of them will be less than the other. So we will use that structure. So let us take 2 continuous functions f and g from u to r. Let us produce other function, not necessarily continuous, we do not really know that yet. We can write a function first of all, u to r, it is defined as the following: x goes to, look at f, x an element of u, so f of x will be an element of r. So, we will take that. G is a function from u to r, x being element of u, g of x is element of r. So, that gives other element g of x. Previously what we have done is, we have put some plus here or dot here or minus here or divided by here, whatever we have put. We did not put the order structure here, right. Let us put the order structure now. It can be this, it can be this, there are two options. So, the order structure that we are putting is the following: I consider this set and take minimum. It may be fx may be less than gx or gx may be less than fx, but this one element I will get. See, minimum is not special, one can replace this by maximum. And is it a continuous function? Is minimum of two continuous function supposed to be continuous function? This you will do. I will not do this. You will do the other part also. Given two continuous functions, the minimum is a continuous function, maximum is a continuous function. How is it defined? Let me write down this minimum of f comma g is a map from u to r, defined as an element x belongs to u is mapped to the element in r, which is by definition minimum of fx and gx. That is what is this notation means. One can replace, as I said, one can replace this minimum by maximum, and here this will also will change to maximum. So, this is one more way to construct continuous functions from old continuous functions. This you will see multiple times. Yeah. So, construct of new examples from old examples will improve your understanding of the whatever idea, irrespective, not necessarily in analysis, in any course, this you will see multiple times. This will improve your understanding. So, that's the one reason why I want to focus on this word construction. That given the old examples, you produce new examples. We have done two such examples here. Let us do some more, or maybe at least one. The question is, what property should I use? I have used all the four properties, the addition, multiplication, all those maps of R. Then I used the order also. What else is there to use? If you are seeing it as just R, then maybe these are the only things. Of course, you can do this root of f, right. We have said that completeness of R, with using that we have produced some elements, root of 2, root of a for a positive, this we have said already. So, if f is a map from u to R such that f of x is positive for every x belongs to u, one can talk about root of f. This is a function from u to R, x is mapped to root of fx. Because fx is positive, only for positive elements of R, I know what it means. For other elements, I do not know what it means. So, I will focus my attention to this case. So, now the question is, if f is continuous, is root f a continuous function? One can talk about root f, cube root f, nth root f, whatever you want to do, because all these elements you already know they are in elements of R. So, use that. So, now we have many examples of continuous functions. Are we happy yet? No, not yet. There are many other examples of continuous functions. As I said, we have used all, it seems we have used all properties of R. We might have used all properties of R, but we did not. But there is still one thing that is remaining. We did not use the property of functions in the following sense. Given two functions, we can produce other function. You might have already guessed guessed whatever I am saying. There is a notion of composition of two functions. Let us write down that now. So, given two functions u2r and v2r, let me call this f, let me call this g. Suppose f of u is subset of v, then I have a function that goes by the name of g compose f, a map from u to r that is defined as x goes to g of f of x. This is a function. This is a function produced from these two functions. So, whatever I have done till now is just using the structure of R. Now we are using the structure of the functions. Functions has this property. Given two functions, if they satisfy this condition, then one can talk about their composition. Now the obvious question is this: if f and g are continuous, is the composition continuous function? This is what you need to check. This might take some more time, because the previous examples, whatever I have said about addition and all that we have already done for sequences. Addition of two sequences that are convergent is convergent, all that we have already seen. But this you might have to spend some more time to understand why this is continuous, because we have not done used the convergence techniques in this point of view. So, maybe there is a necessity to give some other description of continuous functions, not in terms of sequences. This is one example, that if I try to use sequences idea here, it might take some time. We want to save some time. So, we will see some alternative description of continuous functions, and then see that in one of those this is very straightforward, not even 1 or 2 lines. Once I tell you the description of the alternate description, you will immediately say, okay, yeah, this is true. But for if I am looking from the point of sequences, it is not very clear. I mean, how do I even proceed? So, that is all for today. In next session, we will see the other description of continuous functions, and some more results. That is all.